Good morning, everyone. I'd like to thank D-Wave for giving me the opportunity to talk to you today. My name is Paul Warburton. I'm from the Electrical Engineering faculty at University College London, and I've been working on superconducting devices for a very long time, and I guess quantum annealing using those devices for 10 years or so. So what I'm going to talk to you today is about quantum annealing and power consumption, and I'm going to look at a particular case study in mobile telecommunications, somewhat following on from the previous presentation of Anna-Rita, where we asked the question, can we consume less power by doing computation with quantum annealing? So this work is a collaboration between my group at University College London, also the group of Carl Jamieson at Princeton, and John Kaywell at Interdigital. And most of the quantitative work I'll be talking to you today about was done by Srikar Kasi, whose picture you see here. He's a PhD student working with Kyle at Princeton. And we have published the work in this IEEE transaction shown here. So if you want to know more of the technical details, do take a look at that article. Okay, so I guess there are many reasons why you might want to use a quantum computer, and I'm going to list three of the obvious ones. Firstly, you might want to do a computation that simply cannot be done classically, and that's what's behind Shor's algorithm, which I guess is the driver for much research in gate-based quantum computation. And also we heard yesterday in Andrew King's presentation in quantum simulation, he is now using the annealer to simulate something that simply cannot be done classically. Another reason you might want to use a quantum computer is that you get a better quality computational solution in some sense. So maybe it doesn't get you there faster, but it gives you a better solution. And one example, I mean, there are many of these that I like to focus on, is if you want to sample from a Boltzmann distribution in an unbiased way, there are ways of doing that with a quantum annealer, and I refer you to this paper here in PhysRev Applied from the Los Alamos group of Carlton Cofrin for more information on that. But the third reason why you might want to use a quantum computer is one I'm going to talk about for the rest of the presentation today. And that is that quantum computation can deliver a solution to some computational problem at a lower cost. And in particular, if you can reduce your power consumption budget while still delivering an equivalent quality solution in the same amount of time as a classical computer, then that's clearly a win-win situation for a quantum solution. And I'm going to, as a sort of case study, look in particular at the mobile telecoms industry. And here's a slide which I've taken from this review by Schneider Electric a few years ago now, looking at the evolution of the worldwide annual energy demand by the information and communication technology sector. And you can see, you can see that there's a strong increase in the amount of power consumed. And just to give you some idea, so this is 2030 at the end here, where there's a prediction of over 3,000 terawatt hours of electrical power consumption just in the ICT sector. And this dark blue color, which I guess is this one, is mobile telecoms networks, which I'll talk more about later. And just to give you a reference, this line, I think, has moved in the editing process. This is the total electricity consumption in the UK, which I think should be a little higher than that in 2023. And up here, the total energy output is equivalent to about 500,000 wind turbines. So there's a lot of energy consumed in the ICT sector. And where is that energy going? So all the computation at the moment is done by conventional classical silicon CMOS technology. And the key takeaway for silicon is that the power dissipation when you're computing something is simply proportional to the number of operations per second. By operations, I mean, very simple arithmetical operations like addition or inversion of a Boolean logic. So the silicon industry, of course, has been very good at decreasing the amount of power consumed per second as various iterations of the silicon technology node develop. So here you see, for example, if we look at the 1.5 nanometer node, which is coming into line in the next 5 or 10 years or so, by reducing the supply rail voltage, which we see in the second column here, you can get up to around 2 times 10 to the 11 operations per second per watt. And that's the relevant unit because, as I say, if you switch a silicon transistor faster, you will consume more power. So that's the story for CMOS. Now let's have a look at what happens in a superconducting quantum computer, and this applies to quantum annealers and gate-based machines. So the power consumption of a superconducting quantum annealer is completely determined by the power of the dilution refrigerator. So your qubits are sitting at 10 millikelvin, and you need some energy to cool them down to that temperature, 0.01 degrees above absolute zero. And that's about 25 kilowatts, and the key point is that that's irrespective of how much computation you're doing inside the dilution refrigerator. So we conclude that if there's any computational task that would consume more than this 25 kilowatts with a classical computer, then you really should be thinking about doing that on a quantum computer in order to save your electricity bill. And if we look at how much computation you can do with 25 kilowatts, looking at this 1.5 CMOS node that's coming in, let's say, 5 years or so, you can do about 2 × 10⁻¹1 operations per second per watt. And so any computational task which consumes 25 kilowatts corresponds to around 6 10⁻⁵ operations per second. So if you've got some computational task that's going to need more than this in terms of operations per second, then there's a case for using a quantum computer. Okay, so what I'm going to talk about in the rest of this presentation is this case study in mobile telecoms networks, and I'll be talking about 2 particular computationally intensive tasks in a future mobile telecoms network. And I'll ask the question, what technological developments do we need to look at in quantum annealers in order that we might use these for these computational applications in mobile telecoms and cut your power bill. Okay, so now drilling down from the same report I cited earlier on from Schneider Electric, here's a look at the global energy demand in mobile telecoms networks from 2015 and then a future look to 2030. And you can see that if you look at mobile telecom networks, the power consumption per year in terawatt hours is rapidly increasing as we go to future mobile telecoms implementations. There are 2 particular computationally intensive tasks in mobile telecoms that I'll have a look at. Firstly, you have MIMO detection. So MIMO stands for multiple input, multiple output. And I'll also talk about error correction decoding. At the moment in our existing mobile telecoms networks, these are not the power bottleneck. Most of the power in your mobile phone networks is the radio frequency energy that you're using to route your calls around the city. And the computational tasks today are comparatively less power hungry. But if we look on a 5 or 10 year time scale, then as we showed in our paper with Princeton, these computational tasks, in particular the MIMO detection, are likely to become the power bottleneck. So first of all, let me talk about MIMO detection. So MIMO, as I say, stands for multiple input, multiple output. And the idea here is that you're using spatial multiplexing, using different regions of free space for transmitting your mobile data in order to maximize the spectral efficiency of your mobile telecom system. So here's a cartoon that I've taken from this paper in which, sorry, I've gone forward there, go back, in which we have M antennas at the base station, multiple antennas, M of them, servicing K users nearby. And these users can all be using the same frequency of the channel at the same time. And by looking at phase information of the different signals received at the antenna, you can demultiplex these different signals from the different handsets. So at the moment in 5G, M is bigger than K, so you have multiple antennas per user. This is called massive MIMO. And the reason for that is that the demultiplexing is comparatively straightforward. It's a sparse matrix inversion. But the downside of this is that your spatial multiplexing is not fully utilized. And if you look at the state of the art at the moment for 5G, we have m equals 4k. In other words, for each user, we're on average using 4 antennas at the base station. So in future, maybe 6G implementations of MIMO, which is called large MIMO, we want to move to a regime where m equals to k. In other words, we have the same number of users as we have antennas. And this is going to make the deconvolution of the signals received at the base station computationally much more challenging, which I guess is good news for potential new computation techniques. And the advantage is then that you're making full use of the spatial multiplexing of this base station. So this is, in terms of a network operator, this is going to maximize the number of simultaneous users you can have per base station. So the computational challenge is as follows, and this is a Cubo formulation of how you do the MIMO decoding operation with quantum annealer. And you have to minimize this cost function, where y is your received data that you receive at the antenna. H is some wireless transfer function matrix, which describes where all the calls are coming from in your network in that particular base station. And then you're trying to calculate x, which is the original transmitted data for each of the handsets. So this is an optimization problem. Those of you who know a little bit about these sorts of problems already will realize that the killer, as we'll see later on, is this squared term here. And I'll talk more about that later. But this is a Cubo formulation. And in principle, you could put that onto a quantum annealer to do your MIMO decoding. OK, so this is what we want to do. It's classical algorithms exist for MIMO decoding already. And the state of the art is this classical sphere decoding algorithm, which was proposed by Damon and colleagues, I guess, 24 years ago now. And if you put in some typical parameters for 6G future mobile telecom network, you need about 10 to the 8 decoding instances per second. And if you look at how many operations you need per decoding instance, you get around 10 to the 16 arithmetical operations per second using this sphere decoding algorithm on a classical CMOS computer. So if you then plug in how much power that will consume in the future 1.5 nanometer CMOS node, you get about 43 kilowatts. And that's good news for us, for this presentation at least, because that is in excess of the power consumption you need for your dilution refrigerator. And that means, in principle, if we can get this to work on a quantum annealer, we can consume less power doing this MIMO detection algorithm. So that's the classical case. How much power is consumed by a quantum annealer, and what would we need to get there? So for a single decoding instance, it turns out you don't need so many qubits. You need fewer than 1,000 qubits for these typical parameters for a 6G mobile telecom MIMO detection. However, the time requirement for each of these instances is around 40 microseconds plus 2 microseconds per sample. And I'll drill down into where these numbers come from in the next few slides. But if we just take that as read for now, then in order to achieve this 10 to the 8 decoding instances per second, we could, for example, run the D-wave annealer or a quantum annealer once with 3.9 million qubits, which basically reproduces the same problem in trivial parallelism many times. Or if you wanted more samples to improve your signal to noise, you could do 20 samples and around 7 million qubits. So this is clearly beyond what we have today, but as I'll show later on, I think is technically feasible. And as I said, if you put this in a dilution refrigerator, the power consumption will be 25 kilowatts, which is a good deal less than what will be consumed doing the same computation with this classical algorithm. OK, so just how feasible is this? They seem like large numbers of qubits. So I'm going to talk about whether we can do the computation quickly enough on a quantum annealer, whether we can scale to around 4 million qubits per fridge. and then I'll talk about the qubit couplers that we need to do the MIMO detection. Okay, so first of all, timing, and here's a pretty standard diagram of the timing on the D-wave quantum annealer. You have some problem, you have to program your quantum annealer. That takes some time, as we'll see in a second. You then have 3 stages per sample, which you repeat some number of times. There's some post-processing, and then you collect solutions. So we'll first start with the programming phase. What does this consist of? You basically have to set all the qubit and all the coupler bias parameters, and currently that takes of order milliseconds, but I think in principle, if you extend this to the future, your programming time, in other words, the time taken to program all your qubits and couplers, is ultimately limited by the bandwidth of the control lines that run down from your room temperature control electronics to your superconducting quantum processor. And so if we plug in, again, the numbers we think we might need for this MIMO detection problem in mobile telecoms, we're going to need around 1,300 radio frequency coaxial lines leading down from room temperature to the 10 millikelvin stage of your dilution fridge. So that was the programming time. We then look at the sampling time, which gets repeated a number depending on how many samples you're doing. First of all, we look at the anneal time. That can, in principle, as we heard yesterday in Andrew's talk, be on the order of tens of nanoseconds. The readout time, where you read out the state of your qubits at the end of the anneal, currently is tens of microseconds. One could project that to be a bit faster, maybe 1 microsecond or so, which has already been demonstrated in a smaller scale annealer by the QEO collaboration a few years ago now. And then a readout delay, which is basically allowing your qubits to reset themselves before the next sample. Currently, that's between tens of microseconds to milliseconds. And again, if you do active reset, which exploits this Purcell effect, we think you could get that down to around 100 nanoseconds. So if you add these together, you get some number like 2 microseconds per sample or thereabouts, projecting forward. So the total projected computation time, for instance, could be roughly 40 microseconds to do the programming and then 2 microseconds per sample. This will take some technological developments, but it's certainly within the possibilities. Okay, so the timescales seem to work out. What about the qubit numbers? So we said we need around 4 million qubits per fridge to do this MIMO detection problem, given some typical parameters of a 6G mobile comms network. Physically, they will fit in the fridge. So if you take, for example, a Blue Force XLD dilution fridge, you can get about 14 million qubits in the area of the mixing chamber where your superconducting chip sits. And we need around 120 RF coaxial control lines to bias these qubits. And if you look at the static heat load, which these control lines, so these control lines, of course, are short circuits for thermal energy coming from room temperature down to your fridge. But again, you don't worry too much about that, because that can all be carried away by the typical cooling power at the millikelvin stage. And the physical space of the RF connectors, again, suggests that these will physically fit into your fridge. So in terms of the qubit count, again, this seems feasible. It'll take some engineering development. What's tricky for this is the fact that we need all-to-all qubit coupling. So because of the squared term in the QUBO cost function that I was looking at earlier on, we need all-to-all coupling to implement that. Of course, you have 768 qubits for these typical number of users and antennas and so on. And that suggests you need around 300,000 couplers per instance. You have multiple instances of these sitting on your superconducting hardware, and so you need around 10 to the 10 couplers per fridge, exclamation mark. So this, I would say, is the biggest technical challenge in tackling this problem. I mean, it's also partly why, of course, it's difficult for classical computation. It's the same challenges faced there. It's a highly connected system. Of course, there are ways around this with minor embedding, which is a standard D-Wave type approach, or possibly this approach for parity embedding, if you like, by Wolfgang Lechner and colleagues, which I refer you to this paper. So this is the main challenge, I think, because it's a fully connected graph, we need a large number of couplers. So that was about MIMO detection, which is probably the most complex computational task in future mobile networks. I'm also going to just touch briefly upon error-correcting decoding in what remains of my presentation now. Okay, so what is error correction decoding? This is for classical communications. Of course, error correction is a major research topic for gate-based quantum computation, but here I'm talking about a classical communication system. And the idea is you've got a communication channel with some noise on. You want to transmit data across the channel and recover the original message from your source data, even in the presence of noise. So the way you do that is you take your n bits of data and you encode that by adding some redundant information, typically in the form of parity check bits, to your data. And then you transmit m bits through your channel where m is bigger than n. Some of these bits get corrupted by noise, but still you can decode your original signal by decoding at the receive side to recover the original n bits. And this box here with the decoding in it is what can be done with a quantum annealer. And in fact, I've published papers on this many years ago now as a proof of concept. So the decoding is where we think the annealer can play a role. Decoding, again, is a hard computational problem. If we look at the classical methods for doing this, which is this belief propagation algorithm, again, we estimate we need around 2 10 to the 14 operations per second. And the power consumption using the CMOS figures is a little under a kilowatt. So this is a less power-hungry application, but one which we think is addressable with a quantum annealer. If we look at the resources we need for the quantum message passing algorithm, again, using similar numbers for our parameters that we had before, we need a large number of qubits, around 21,000 per instance, but we don't need so many of them, I guess. So we might need, if we wanted 1 sample, that would take around 1 million qubits, or if we wanted 20 samples, that would take around 2 million qubits. Of course, the assumption here is that we're already doing MIMO detection in the fridge. And so the additional power consumption by doing this error correction decoding is effectively 0, because you can put more functionality into the fridge at a power budget which is purely set by the power taken to cool to 10 millikelvin. Okay, so I guess I've reached the conclusions of my talk. Hopefully I've demonstrated the following, that I think superconducting quantum annealing has the potential to deliver cost savings due to reduced power consumption in some computationally highly intensive tasks. And the one, in particular, this ballpark figure of around 6 10 to the 15 operations per second is the benchmark where if your classical computer is computing at that rate, then there's a gain to be made by putting your computation into a dilution fridge. If we look at the 2 particular applications in mobile telecoms I spoke about, this multiple input, multiple output detection algorithm, I think it's a challenging one because of the all-to-all connectivity, but that really does have the potential for power savings that when you compare with classical computation. And again, there are many technical developments that would need to be done to deliver these, with improvements in programming time, readout time, and qubit reset time, increasing the number of qubits, and again, this all-to-all connectivity that I mentioned. So that's all I have to say. If you want to know more about this, please feel free to speak to me during the coffee break, and also take a look at this publication in the IEEE transactions. Thank you very much for your attention.